The good news is that in an hour I can go to sleep and you guys can get on with the rest of the class and stuff. The bad news is you've got an hour of me ranting about various things in this whole business of dynamos, plus some very interesting things. I think the sort of cause of MHD's own demise is an interesting idea. The point of this slide is just to show you that much of the work on the generation of a solar dynamo of this kind, alpha effect, omega effect, the omega effect is concentrated in the regions of shear in the interior of the sun. But when we look at this plot here, there was a suggestion many years ago by Durney that some of these things are associated with a shallow surface shear layer. Remember, shear is everything in amplifying the magnetic field in the induction equation, and that this one is to do with the deeper part. So, in effect, the sun should really have appeared down here in these kind of models because there's no surface shear layer. On the other hand, that's been introduced into those models that I know of. On the other hand, we do have this surface shear layer, and if one takes across this gradient, one sees almost a radial plus polar kind of dependence of the shear here. Those gradients, it's not flat, quite unlike this, for instance, which is completely flat. There's no gradient here. We'll come back to this in a short while, actually, because it means there's essentially no gradients in the velocity whatsoever. So if I take the gradient of the Maxwell stress, it's zero. Therefore, there's no actual force that can be imposed as a result of grinding against that to do work against the magnetic field. Okay, we did reconnection just a little bit. I don't want to underestimate. I mean, there are people who've worked professionally in reconnection for their entire careers, right? I mean, I'm just introducing some of the concepts there so that we kind of complete the circle of things that Fausto was talking about a little bit, at least geometrically. There's a very interesting article, and I put this one on the website. Oh, by the way, apparently all my view graphs are there on the website for you guys to ignore. And but there's a very nice article written by Gene Parker, 2009 Space Science Review. It's on the website for you guys, on my website for you to look at in those materials. So, I mean, this is a very provocative title, right? The state of our knowledge and ignorance. Ignorance is not something that we like to talk about too much, but he brings attention to this. So we review some long-standing scientific mysteries related to solar magnetism, with final attention to the mystery of the turbulent diffusion that is essential for the theoretical alpha-omega dynamo that is believed to be the source of the magnetic fields of the sun. Fundamental difficulties with the concept of turbulent diffusion of magnetic fields suggest the solar dynamo problem needs to be reformulated. I mean, oh my God, this is really bad news, right? And if he's right. So what I'm going to do is I'm going to go over his argument a little bit, and it relates nicely to what some of the things Fausto talked about with regard to Lyapunov exponents and what have you. So again, we're dealing with just, if we just look at the induction equation, there's no forces in this. This is just for a given velocity, this is what the magnetic field is going to do. That's all it describes. And here are the various shear motions that enter into the curl term. And we can look upon this as a source and sink kind of thing. Here is the source for dBdt, and this is the diffusion operator. It's going to get rid of the magnetic field as best it can with a time scale associated with the diffusivity. So, okay, let's just remind us where we are. So again, induction equation. Let's have a quick look at some numbers in here, quantitatively, instead of just presenting other people's results. So from seismology, we can define a stretching time, which is simply, if I take one of these shear gradients that's measured, and I look at the change in velocity, and divide it by the distance over which it's changing, I get a time scale, okay? And this gives us a time scale of about 5 days for the for the gradient in differential rotation as a function of latitude, just above the core region of the sun in the convection zone itself. So what does this mean? It means that in 5 days, we will have stretched out a field line very considerably as a result of differential. If we had to put a poloidal field in there, it would have been stretched out very significantly in that period of time. Now, in order to get a cycling dynamo, you can kind of ask the question, just on the basis of this equation, to get a cycling dynamo, we sort of need to have a battle between the source and the sink that's going to lead to a certain time scale for the evolution of the magnetic field. And if one looks at the situation and just says, well, I wonder what we really need in the way of an eta to make this thing work in a cycling sense. So you have a time scale here. You have a time scale here of 5 days or so, and you have another time scale here. Well, you end up with a situation in which you say, well, we're going to end up with a diffusivity such that if we're going to use this to amplify the field, we're going to end up with a diffusivity on the order of T stretch divided by Rm, and we're going to use a number on the order of 10 to the 3. That comes about because of we want to get this 10 to the 3 times bigger than that. That gives us about 5,000 days, about 11 years or so. So we want a pretty significant time scale here. So if we put those in, we end up with a magic number of about 10 to the 11, 4 10 to the 11 centimeters squared per second for the diffusivity. And that's typically what people use in the models of the sun, right? Otherwise, you don't get this kind of period. Okay. Now, one way to look at this is to say, well, it's an eddy speed times a distance a given eddy moves. So you're just taking a piece of magnetic flux, and I'm moving myself over here, and I'm doing it in a time t, which is the distance divided by the time I take. And the product of those two things gives me the diffusivity. And this comes from the idea of smoke mixing up particles, tracer particles in hydrodynamics. Okay. Now, this came across from Fausto's lectures in a slightly different way. This came about because of the scale separation between the large and small scale, and by expanding making some assumptions about the correlations between the small scale magnetic field and the small scale velocity field. And then he wound up with an expression which gave an alpha effect as a source term in here for the mean field. This is the total field, but for the mean field, he ended up with an alpha B here, and he ended up with an eta thermal plus eta diffusion there as a result of the mean field theory. So that seems to be fine. But it should be worrisome a little bit if you think about it, because that eta came from the small scale correlations between velocity and magnetism. In the momentum equation, you have the change of momentum by d time equals some pressure terms, etc., gravity, etc., plus the Lorentz force. So the rate of change of the velocity of an element of fluid is somehow correlated to the Lorentz force in it, and that hasn't been addressed actually in the mean field theory at all. It may be, for instance, that the velocity is all in that direction, and the magnetic field changes are all in the other direction, so you end up with a essentially zero correlation. Or, in fact, probably perpendicular would be a more likely thing to give you zero, otherwise you get a full anticorrelation. So this business of deriving a turbulent diffusivity on the basis of mean field equations has to be looked at, whether you like it or not, in terms of the dynamics on small scales. And the reason for that is that the Lorentz force is proportional to the curl of B, which is like B divided by the length scale. So as we go to smaller and smaller scales, we better damn well make sure we're taking care of the Lorentz force, even in a very high beta plasma, where the magnetic field, ostensibly on average, is much smaller in its stresses than the gas itself. Okay, so we're going to look at that. So this is basically saying what I said just now. And as I said, it's a prescription to get order from chaos. But let's look at this in a little bit more carefully. So to summarize then, in order in order for Goldilocks to get the porridge the right temperature so she can eat it, in order for us to build a model of the sun that works in this kind of mean field kind of thing, we have a discrepancy of 8 orders of magnitude. And this is kind of, at least to me, somewhat worrisome. And in fact, Parker, when I thought about this, and I came across this paper by Parker in 2009, that's the wrong date, but I guess he wrote it then. So what's he doing? He's examining the kinematic assumption on small scales. He was actually following some work in 2 dimensions that Cattaneo and Weinstein did in 91. And his argument goes as follows. Unlike a scalar field, magnetic flux is conserved. So even if we have a little bit of reconnection in certain places and strong gradients in which the magnetic field diffuses, if that's very intermittent, between those regions, if I put some plasma and put a magnetic field through it in a flux tube, that flux tube maintains its identity. So between the places where the diffusion is going on, we have a topologically invariant magnetic field, and we can label that magnetic tube by the plasma glued to it all the time. So what he does is he says, well, let's take this dynamics. And remember, Fausto thankfully talked about the Lyapunov exponent kind of dynamics at small scales and hydrodynamics. And let's assume that we're in a kinematic regime to start with, so the magnetic field is not dominant at all. Let's just use hydrodynamics. And what he does is he says, well, we know in hydrodynamics that the initial magnetic field will get stretched out by these fluid motions. Because it's frozen to the fluid between the regions where it diffuses, we're going to end up with an exponential growth in the field strength on small scales. Again, this is kinematic to start with. Well, he makes an argument that so the length goes like this, the thickness goes like this, which conserves the flux in the sheet itself, in this small tube, flattened sheet of, or whatever it is, of fluid. Now we just ask the question, what does it take for diffusion to set in versus what does it take for, like, say, a Lorentz force to start kicking in? And what you find is, as usual, that dissipation, this Rm to the half, always shows up, right? So, I mean, when you do the sums, in his paper he shows you, if you're interested, you should read it. So when this gets to a length scale or a thickness scale, such that we have this term, then dissipation occurs. In other words, when it's stretched out to a certain length of an eddy size, then it's got down to a thickness such that dissipations will start to occur. And that occurs when the magnetic field is increased by Rm to the half. But the problem is that the magnetic stresses themselves have increased in proportion to the magnetic Reynolds number. It's B squared, not B. So his conclusion is that if one is to look at the small scale in hydrodynamics and look at the initial kinematic growth of the magnetic field, before it gets to the point where it can dissipate, you better deal with the magnetic stresses. Now, Parker has not solved that set of equations in a numerical thing. He doesn't do that kind of work. But what he's arguing is, forcefully, that actually this is a general problem sufficient that at very high Reynolds number, we've got a factor of Rm to the half at which the Lorentz forces start switching off the diffusion before it can start. Okay? And he's arguing it's necessary to rethink the entire dynamo for the sun. Well, let's think about what this diffusion really is. If I have pure kinetic theory, my electric current density, what is the diffusivity eta coming from? It's 1 over mu 0 sigma. Sigma is the solution to the equation of motion for the electrons relative to the ions, in which you neglect the electron inertia. In other words, the electrons relax so fast that you can replace the dynamics of the electrons with the rate of change of momentum of electrons is basically the momentum of the electrons divided by collision time equals the force on them, which is the electric field times the electron charge. That's where you get J equals sigma E from, okay? And so what this means is that this eta term is basically, on a kinetic scale, something which separates electrons from protons. It's a drift speed of the electrons. So if I, in fact, invoke through magnetohydrodynamics something that's not thermal but is a different parameter, am I really separating electrons on those scales? Well, no, we're not allowed to do that. That would create an enormous effective electric field to do so. So something, in other words, this would be very much larger. So we can't actually envisage this as anything like a ohmic diffusion. Ohmic diffusion is the destruction of ordered motion of the flow of electrons relative to the protons or the ions into thermal energy. Whatever this turbulent diffusivity is, it's very different. I don't think I have much more to say on this subject in terms of turbulent diffusivity, except that it comes from the best answer I can think of is that it comes from a kinematic mean field approach to the induction equation alone. And it's not clear to me if something happens in the dynamics of Parker's, when you include the momentum equation, if it's really going to be capable of switching that off and be important on a global scale. Most solar physicists just flat out ignore this. This is not of any interest. What they find is that this Goldilocks value I mentioned, it occurs all over the place. This is the number that you need down in the interior of the sun to make the balance between the omega effect and the alpha and the dissipation about right. So it's the shear layer. It's also in the alpha effect. It needs to be of this value for the thing to evolve in time, incompatible with the way the sun does it. On the surface of the sun, what amazes me is you read the literature on what forms a coronal hole. This is a pattern of magnetic field on the sun that exists for months, many rotations at a time, in which somehow the sun wants to be unipolar. In order for those things to exist against meridional circulation and other differential rotation and all these other things, you have to plug in a diffusivity at the surface so you can solve the same induction equation, prescribe the velocity fields, and figure out what AT you need. And the AT you need turns out to be the same as this, as the interior. And that's really strange in my mind, because in the interior, one is dealing with magnetic fields that are far below the equipartition value in an average sense. Maybe it's the fact that the equipartition is not the really interesting thing and that it's dynamically important on concentrated scales. But in the surface layers, where we see the coronal holes, the magnetic field is everything. I mean, it dominates the stresses. And yet we still get the same answer for the diffusivity in order to account for this evolution of surface fields on the sun. If it were much larger than this, we wouldn't have solar flares. Why not? Well, if we poke up a magnetic field out of the surface and you want it to interact with previously existing field, which is going to happen as field blobs up from underneath, as a result of the magnetic field being strong, the plasma gets evacuated, there is an instability that sets up called the Parker instability, in which it becomes buoyant and it rises through the surface, and that's what leads to the sunspots, apparently. At the moment, we don't know what concentrates the fields into those very strong values needed to make that happen down in the convection zone somewhere, but there are various ideas out there for that. But what amazes me is that if we were to blob up these things into the corona, and we had a diffusivity that was, say, merely an order of magnitude higher than this, that would destroy all the gradients in the magnetic field there, get rid of all the free energy, ohmically, not ohmically, but it would redistribute it over the surface such that the ability for storage and release of energy inside a flare of a certain length L in a time t would never happen. So there's something very interesting about this way of looking at things. Perhaps a different way of saying it is that in our naive fashion, in my naive fashion at least, if I only look at the evolution of the magnetic field in terms of these things, I'd better be very careful not to ignore the momentum equation at the same time. In other words, it really is a magnetohydrodynamic system, not a magnetokinematic system. So this is an area for research, I think. I mean, I'm trying to be provocative here. Okay. This is great. I may even finish early here. So let's put that aside for the time being. So that, to me at least, there's a worry about what the actual behavior of the sun's magnetism does at various depths and heights above the sun in terms of a diffusivity. And I think this is an area worth looking into in more detail for people that are a lot more clever than I am. Now, what Spruit did in 2010, he won the Hale Prize, which is the highest prize you can get, at least in the United States, for advances in solar physics. And Spruit is is currently in the Max Planck Institute. Did a lot of work on flux tube dynamics, all kinds of interesting things to do with magnetohydrodynamics in the solar atmosphere and other places. But he basically took a new look at the solar dynamo and basically came up with a very severe criticism of the picture involving these diffusive mean field kind of approaches. And so let's see what he has to say. Well, so Spruit basically looks at the mean field dynamos, and these are the ones that have the success of producing the butterfly diagram and the ones that go into the poles. Okay, you're not going to generate sunspots, but maybe you can say, well, maybe we don't care too much about that, unless you really believe that sunspots really are the primary signature of the dynamo process itself, in which case you've got it completely wrong. And that's what Sprout's saying, I think, at least to some degree. Okay, let's follow through his arguments. So what does this mean? He's saying that in the mean field dynamo theory, we have basically these concepts. And so, you know, you're looking at the detailed dynamics on separation of scales, you're looking at correlations, and you're looking at helicity to do the job for you on these very small scales in generating an oscillating dynamo using an alpha and omega effect. So I think we've understood pretty well what the sun is doing there. So instead, Spruit claims that the business of making a toroidal field out of a toroidal one is almost trivial. The induction equation shows you that if you stretch the field lines with differential rotation, you've got to generate magnetic field. And if you have a little bit of reconnection, no matter how that works, you're going to have to generate strong magnetic fields at the base of the convection zone. So he's saying that aside from all this stuff here, with the machinery of building an induction equation for the mean field in terms of correlations between the small scale stuff, and then you write those in terms of the mean quantities themselves, that stuff is misleading. And he says it because it is sufficient that, first of all, that a star rotate differentially. So that's the omega effect. And then, because it's rotating differentially, it's rotating, therefore you have a Coriolis effect. Therefore, no matter what, you're going to get an alpha effect. And as I understand it, his argument is that essentially the alpha effect need not be explicitly built into the small scales. You can actually, like that simple picture I showed you of the conversion of the toroidal into poloidal field, you have a large scale twist of the field, and we see it in sunspots emerging at the surface. And that is sufficient if you can propagate that twist to the source regions where the omega effect is happening with alphane waves, then you will, if you then can make reconnection happen, you will generate a dynamo through this nonlinear growth of this thing without having to appeal to anything on small scales at all. And on that basis, he's basically saying what he says it much clearer than I just did. The dynamo depends on the finite amplitude of the field, which determines the time scale of buoyant magnetic instability, leading to the alpha effect. And this is, in fact, compatible with critical data. Remember, I started talking about critical data. Well, this is one of his main plots here. What this shows is sort of the inverse of that stretching time I argued about earlier, as a function of latitude. So what he's doing is he's putting a poloidal field inside the convection zone. He's using, or throughout the sun, he's using the differential rotation observed down near the base of the convection zone, and he's using the latitudinal shear to find out what the rate of growth of the magnetic field is just from that shear stretching term. That's all it is. But what's interesting here is that you get a peak around 55 degrees. So what he's saying is that as I go from equator up to pole, I do very little generation of magnetic field at this point through the differential rotation, but I generate a lot of it up here. So where are the fields going to appear absolutely first? Well, this is the growth rate. They're going to appear first at the peak of this thing here, somewhere near 55 degrees. That's not where the sunspots are. The sunspots are down here, and they migrate down here. So what's this got to do with things? Well, first of all, the dynamics, this is only a local thing at the base of near the base of the convection zone. It's possible, I guess, that the dynamics of this thing would emerge not radially, but perhaps in an equatorial direction, and that would account for the formation of sunspots. But in fact, when you see those synoptic maps of the sun, there are regions where there does appear to be some generation of magnetic field up there, which normally is assigned to the diffusion of field away from sunspots lower down, but which could in principle be due to the fact that buoyant magnetic fields, if you crank up the magnetic field enough, you evacuate the tubes for pressure gradient, for pressure balance, and then these things become buoyant and rise up. When those things happen, it could be that these things are kind of dispersed somewhere near this latitude. And in fact, there is evidence in some of the data coming out of coronal and other things that there is some significant source of magnetic field around these latitudes. Okay. Another thing that Spruit pointed out, we did see this movie the other day. I have no idea why it's not working. Well, is that the surface appearance of the magnetic field comes in these strong things called spots. Furthermore, as they emerge through the system, there's a separation between the spots, and this is due to the fact that you've got these loops emerging through the surface, etc., etc. This is anything other than a diffusive process. If diffusion were that important, literally that important, you'd have to reverse the arrow of time, because there's no way in which you can separate out fluids. It's like unstirring a cup of coffee, right? And so what's going on here is a diffusive process is one in which the entropy of the system is forever increasing. You're smoothing out gradients and you get rid. So if dB by dt is just eta del squared b, if that's so important, we should see the effects of it somewhere at the surface. And what he's pointing out is, no, this thing is appearing solidly in one big blob, in one tube, and it looks nothing like the result of a diffusive process in the interior. Okay. So, to summarize his complaints about these things, the computing resources needed for a simulation of this whole thing will be available in about 100 years. So, this is sort of an unpleasant thing. What he's talking about is an estimate needed for the disparate length scales between the solar radius and then the length scales at which various turbulent effects happen in the interior to, regenerate and reconnect the magnetic field. The MHD equation completely symmetric to the sign of the magnetic field. There are no flows, no matter how complex, that can separate fields of different signs out of a mixture. And these are just quoting from his paper. And I encourage you to read it because it's interesting, I think. The striking behavior is opposite diffusion. To force it into a diffusion picture, and have to reverse the arrow of time. This rules out a priori all models attempting to explain the formation of sunspots and active regions by turbulent diffusion. The orientation and location of polarities seen in active regions must already have been present in the initial conditions in the layers below the surface from which the magnetic field traveled. So he's talking about there being a strong, very strong dynamical effect deep in the interior of the sun, which survives all the way to the surface without having to travel through the convection zone and acquire more of this helicity via the small-scale turbulence. It's already happened deep down. This is, I think, what he's saying. It's not entirely clear to me. I never heard his talk, but reading his paper, that's what I've taken from it. What I'd like you to take from it is that, along with the paper by Parker, here are two people that are seriously concerned that we're barking up the wrong tree in terms of the physics of the way the dynamo of the sun works. And while we can say, well, you know, Parker's 88 or something and Spruit is 60-something, and, you know, we've got all these young people, these wonderful computers that say something different. You know, I don't think that's a valid criticism here. We have to address these questions head on. I'm not the person to do it. I'm a dumb spectroscopist, spectropolarimeter person. But in the context of a series of classes on the solar magnetic field, I wanted to draw your attention to these things because they're very interesting. I mean, this to me says, hey, we really don't understand stuff. And if you add that plot that I showed you with the sun stuck squarely in the middle, it's telling me that this is a good active research area, and it's going to be so for some time. Okay? There are problems, and he draws his own... he points out that there are some serious problems here to do, and this is what he envisages going on, is that you, through the omega effect, you generate these fields that are very strong. At some point, they become buoyant and burst out. There's a very strong helical effect down here that is maintained all the way up through here. It crosses this convection zone in a relatively short time, dynamically insignificant. The turbulence in here is a red herring. It doesn't really do much to these strong fields because they are in a compressed form already. They tend to reject the plasma around them because they're so strong. So what is this plot supposed to show? Well, this shows you that after a period of time in which this has happened, here are some ones that have happened before that have emerged. So this just continues to pile up and up and up and up. And it has a very handed sign of helicity here. Helicity, remember, is generated by the twisting motions down at the base here, and the opposite sign in each hemisphere. And we have to, the sun has to know how to get rid of this stuff. And the big problem here, as I see it, is that one must actually find out how to get back to a simple situation that we started with, which was an initial toroidal or poloidal field with a simple structure in it. And so Sprout's just pointing out that he doesn't know how this happens, but that this may be a useful way to, if he's right in that all the dynamics is going on deep down, very little going on through the convective envelope and above, you know, there has to be something in the interior of the sun which is actually reversing some of this process so that it can cycle again. And he hasn't identified what that is yet. There are, of course, there is a class of convective phenomena in which you get very strong downflow plumes. So perhaps those are something to do with this. They drag the magnetic field down themselves, back down into the interior. Although this is not discussed by Spruit himself. So I just want to draw your attention to, again, I was mentioning the evolution of surface fields again. So here we go from the interior, where the magnetic field is a small fraction of what's going on, to the exterior, where at least for the first few radii of the sun, the magnetic field dominates the stresses. Once we get above a certain height, the solar wind energy density, rho u squared, is part of the Reynolds stress tensor, which tends to be bigger than b squared over 2 mu above a certain height. So the solar wind is actually that drags the field lines out into straight, pretty much lines that are parallel to the direction of the fluid motion. So the magnetic field is no longer exerting a strength. But if you look during eclipse, if you look with any of the instruments in space that observe EUV and X-rays, you're going to be looking at essentially places where the magnetic field is strong compared with anything in the plasma. Okay? And so at those surface layers, here's just an inventory of some numbers. You know, if we have, I've just pulled them out of the literature. We get numbers between 10 to the 12, a couple 10 to the 12, and I've even seen numbers at 10 to the 15 quoted, which is kind of hard to believe. If you think of that, that's, if we put in, say, a tenth of a solar radius, that's 10 to the 10 centimeters, and a velocity that's 10 to the 5 centimeter per second, 1 kilometer a second, over that's saying that there is stuff diffusing on a tenth of a solar radius systematically on 1 kilometer a second. And the reason they put those numbers in is what they're describing as a diffusion is actually the surface evolution of transequatorial loops and stuff. That's not a diffusion. That's a reconnection followed by dynamic relaxation. So those numbers I wouldn't really take as meaning anything. But I've got to say, I'm really struck by the fact that not only when you look at observations, I mean, this is within an order of magnitude of the same number needed to make the dynamo work in the interior. That's really weird in my mind. And so what these things describe is the rearrangement of magnetic field on the surface. And then in MHD simulations of the surface, okay, these are done under certain conditions of critical numbers, Reynolds number, magnetic Reynolds number, Prandtl number, you name it. But nevertheless, apparently the magnetic field wants to rearrange itself to be perfectly compatible with this. And so everybody says, oh, well, we've solved the problem. You know, we see these kind of, if I put in a granule, it moves at 5 kilometers a second, and it moves 1 meter in, it's one megameter in 5 minutes or something. If you work out what VL is, then you get some number like this. So everybody's like, well, all that's going on is I'm just have a convection cell, and I'm just moving the field lines around like this. And then I have another convection cell, and I move this direction. It's nothing to do with the thermal diffusion and the electric currents involved. It's just a rearrangement thing. Well, I still would maintain that we'd better look at this from a dynamical, not just a kinematic point of view. And these are MHD simulations, so this does have the dynamics in it, but it's done with resolutions that are nowhere near what we have in the sun. The argument is that the Reynolds number is big enough that, well, you get these structures formed, and we don't care about the scale of the very small things. We just care that that kind of energy is dissipated, and that therefore we end up with being able to reconnect, move things around in a certain way, which is compatible with a diffusion coefficient of that. There may be some basis for that in terms of, you know, we have an inertial range. We don't care that we get to this scale because it's all going to scale down to the diffusion length anyway, and we're done with that argument. But remember what Parker said. You get to the point where the magnetic stresses start to dominate before the actual real diffusion sets in. That seems to me to be a terribly important issue to explore. There is another thing, and I'm going to mention ATST here. Say we could measure something very small on the sun, and it lived there for a while. Let's draw a picture of, just for the sake of it, let's draw a coronal hole boundary. So we have radial fields here with odd little things going on here. Then we have salt and pepper fields here, plus and minus, whatever. And we have the solar wind going out, etc., etc. Let's look at something in here. Now, the claim is that together with the meridional circulation velocity plus whatever differential rotation we have here, that eta is on the order of 10 to the 12 is something that will describe sort of the evolution of this thing, order of magnitude wise. I mean, if you want to explain So if I have a little bipole here, and after a rotation, this thing has progressed over here, and it's included this bipole, then this guy, you know, we're going to have emission over there. This thing's been destroyed by reconnection, and you've got material that's gone up and gone down. So now we have a unipolar field. The idea is that, you know, you can describe these processes by this quantity here. This is a prescription for making reconnection happen fast in the context of an induction equation alone. Well, let's really focus on this guy, right? Let's look at a tiny thing here and look at a part of the image in which this thing, an open field, is going to have magnetic field concentrated into what's known as a supergranulation, which is another flow which organizes fields. But it's going to have a root here, and it's going to have tiny little things, which I'm going to draw as a tube. And, you know, solar physicists call these things spicules. Spicules are just things sticking out of the sun that you see in chromospheric lines. Whenever you have a strong enough line that's opaque enough, that forms high enough up, you kind of see the junk that's left out there. And some of the junk that's left out there seems to be coming out in the form of jets like this, like seaweed on the bottom of the ocean sticking up. Okay? So, but now let's look at these things. If we have this as a lifetime of, say, 10 to the 2 seconds, and we have something that is 0.1 megameters across, which is about the resolution that we have, I can work out that L squared over T is on the order of, let's say, this is 10 to the 4. This is 0.1 megameters, so it's 10 to the 2 kilometers. So it's 10 to the 7, 10 to the 14. So this is a length of 10 to the 7 centimeters. So that's 10 to the 14 divided by 100. It's about 10 to the 12. So now, if I believe that this plasma is glued to the fluid as it is between the diffusion regions, I can actually use this measurement of 0.1 megameters on a lifetime measurement of this thing. It's just sitting there doing nothing for 100 seconds, and some of them live this long. I can say that the diffusion is less than 10 to the 12, observationally. Otherwise, this thing would have to be continually replenished by something. And I don't want to invoke, I'm going to invoke Occam's razor. I'm going to say it exists, it's sitting there, and the only thing happening is it has to sit there long enough for it not to diffuse. But if these guys come along, so these so-called experts here come along and tell me that the diffusion rate of the magnetic field in coronal holes has to be accounted for with a few times 10 to the 12, I can present them with a fact that, no, there are things living right at the base of these coronal holes much longer than that. What the hell is going on? They can say, well, diffusion is going on in places where these things don't exist. Okay, now we're starting to get excuses for not addressing, you know, the data. In my mind, so what this tells me is, with ATST, we're going to go much smaller than that. This depends on the square of the length scale. We're going to put hard limits on the diffusion by observing the lifetimes of structures at the base of the atmosphere. And this, I think, is what Parker said when in the year 19, whatever it was, he wrote a report and said this is going to get to the fundamental length scales of important processes in determining the magnetism of the sun. So I would love to see the young people in solar physics look at these things, not from the point of view, oh, I wonder if a spicule is red, green, and blue, or if it's happy, or if it smells, or if it does this, that, or the other, you know, the sort of botany of solar physics, but really the physics of solar physics. And this is a very straightforward thing we can do. If this thing survives longer than what these people say is the evolution time of the large-scale coronal field, we know that what's going on in the large-scale coronal field has got nothing to do with an actual diffusion kind of process like this. Something very interesting is going on, so we've certainly got something to learn. Okay. Here's an example of such things. These are taken in a coronal hole. What this is an observation of a chromospheric line. I don't need to tell you which one. This is megameters, so this is 1 megameter. Many of these things are on the order of 1/10 of that, or a bit bigger, so they're of that kind of scale. These things live 5 minutes, some of them. That's not compatible with what people tell me is the diffusion rate of magnetic field in this system. There's a contradiction. Hooray, I love it when we get a contradiction, because that's the beginning of creativity in science. God damn it, this bloody Mercury orbit, it keeps precessing in a way that's not compatible with Newton. There's got to be another planet. It's got to be Vulcan. It's got to be something. No, it turned out to be general relativity, for God's sake. I'm not saying this is going to lead you to general relativity or anything remotely that interesting. But we may learn something about elementary magnetohydrodynamics by observing things going on in the sun like this. And this is intensely boring. All we're doing is just sitting there taking pictures of things happening fast on the sun, and we're just sitting there and you go. But when you realize what the implications are from the MHD, it becomes rather more interesting and a little bit more profound. Okay. I'll finish up the last 15 minutes with something that I think is one of the most remarkable things. And I'm going to return to Shakespeare again. So this is the whole tragic part of magnetohydrodynamics. Remember, MHD is simply hydro, which means enough particles in a volume, phase element volume, to define statistically meaningful average. We have no problem with that in something like most of the atmosphere of the sun. I mean, there's huge numbers of particles in the volume of phase space. And it also means magneto part is we're going to take, instead of going with a full relativistic treatment compatible with Maxwell's equations, we're going to fiddle with, we're going to keep the Galilean transformations, use Newtonian laws of physics, but we're going to correct them toward a V over C. And that's the basis of magnetohydrodynamics. So, and if providing things toward a V over C are also consistent, it's a perfectly good theory. It should address things on various length scales. So this is the book that I passed around. This is a real heavy-duty thing. This thing's like 400 pages. And it addresses a simple problem that's simple to pose, but the reason it's 400 pages long is that there's no real analytic solution for this thing, and there's just rather more than plausibility arguments that Parker's able to put together. So, you know, it's another one of these situations where if you find you have a thick volume of stuff about something, and it's about physics, more than likely the author doesn't understand what's going on. Because physics should be simple and short, right? I mean, the books by Spitzer and Cowling and people on magnetohydrodynamics and plasma physics, okay, they only talk about certain aspects of those subjects. But if we're dealing with a fairly straightforward theorem, he's written a 400-odd page book here, so it's not complete. But what I want to do is go through the arguments he gives for the sort of poetic consequences of assuming that it's ideal or almost ideal MHD. So we know that the ideal MHD, as time evolves, doesn't allow us to do things like this. The field lines are always threading the same volume of plasma. Okay? One of the arguments that Parker uses is that, and in that he wrote a paper explicitly on this in 1988, is to say that the corona, as seen here, exists because of this business of almost ideal MHD existing in the layers above the surface of the sun in a low beta plasma. And the essence of the argument is essentially that, if I can say that again, the essence of the argument is that is that one has an overconstrained system. You have to find solutions to the force balance equations and the induction equation in ideal MHD. The ideal MHD induction equation forces you a topology which you cannot change. And when you look at those two equations together, only in the most simple configurations can you find a solution in which there are no discontinuities to those equations. In a general case, anything with a little bit of untidiness in it, you're going to end up with tangential discontinuities in the magnetic field. These are called weak solutions to those partial differential equations. They were worked upon by, can't remember the name of the chap in the 50s. Ronnie, do you remember who I'm thinking of? The American guy that... weak solutions to the PDEs of MHD. Famous name, anyway. It might come to me eventually. It's not this funny guy, Fred Hoyle, who's an English astronomer. But anyway, the point is, well, let's get to it. So the real question is, I mean, if we're talking about ideal MHD, where's the energy coming from to transfer it from the plasma to the plasma from the field anyway? Well, it's the approach to ideal MHD which yields its demise. And the idea is that these things form spontaneously as a result of the untidiness of the foot points here, the frozen topology here, which leads to infinitely, in MHD, infinitely thin current sheets. Those current sheets lead to the breakdown of the idea that you've got a fluid with finite volume and mean-free paths and all this stuff. So the theory breaks down because you generate things on such a small scale that something else happens. And that something else is a transference of this electrical current energy into the plasma, namely coronal heating. Okay? So this is a theory of coronal heating. So let's look at this. In the corona, so Parker considers this problem here, zero diffusivity and the limit of zero beta plasma. Let me just show you that again, because there was a question from one of you. Who was it that was asking me about J cross B equals 0 over the break? That was this chap here. Okay. What's your name? Arturo. Okay. Everybody with the name of Arturo, in my mind, is a bit of a genius. There's one called Arturo Lopez Ariste, who showed me some remarkable things in a paper he wrote just yesterday afternoon, or the day before yesterday. Anyway, so let's look at this. The rate of change, complete rate of change of momentum of a fluid element equals I have to be careful here. So here's a momentum equation for a I could include some viscosity here, and then this would be the Reynolds stress tensor or whatever. Okay, but let's keep it very simple. Let's get an inviscid fluid and just have the balance between some forces here. So the question is, if we go into the corona, my argument earlier was that the pressure, if you have a stratified atmosphere, this balances that, and you can ignore that, and you just get an atmosphere like the Earth. And then this is roughly 0 because we're not getting, thankfully we don't have supersonic winds blowing around the Earth very much. You know, that would be a bad thing, in which case this kind of term would be very significant. Let's consider the corona, though, where the magnetic field, because it drops off in a potential way, as say the dipole component of it would drop off as 1 over r cubed above the source region. So these things basically drop out of the equation. That means that we have an equation in the corona which looks like this pretty much. So we have the plasma here, and that is roughly equal to this thing here. So if we start from a state in which this thing is 0, this thing will forever remain. That's an equilibrium situation. Let's start from a state in which this thing is not 0. Let's call it J primed and B primed. Then what this means is that we have the rate of change. If I just replace these with time scales, 1 over tau rho v is on the order of b squared over L. Okay? So I end up with the time scale equals L over b squared rho. So L over VA, the Alfvén speed. Okay? I mean, that's very simple. Okay? So what that means is, if I had this thing non-zero, what would happen would be that Alfvén waves would propagate around the system to try and make it, force it to go to 0 very quickly. because on a time scale of this, which is, if this is, say, 20 megameters, this thing is 2 megameters a second. That's 10 seconds. So that's a very fast time scale in which this thing wants to try and relax. So what it means is that if I wait longer than 20 seconds, I can switch all the dynamics off. It's like ignoring the electron inertia in the electron equation of motion. The electron adjusts itself automatically and relaxes to produce a flow speed which is compatible with the collisions versus the electric field in the equation of motion of the electrons. So on a time scale, if we wait longer than the alpha n crossing time scale, I can actually set J cross B to 0. And that's a good statement. That's an equilibrium configuration for the magnetic field, if one exists. Okay, so let's assume that such does exist. And this is what Parker says. So J cross B is nothing other than if I take the divergence, if I contract with a del operator one of the indices on this, that's equivalent to J cross B. That's easy to show. Okay. The fact is that the stress tensor of the magnetic field with an untidy field line topology, that means they're not all, lined up rigidly like soldiers. They're more like a bunch of Japanese tourists wandering around, a park or something like this. If we do that, it has the curious property of creating internal surfaces of tangential discontinuity, i.e. current sheets, as the magnetic field relaxes to an equilibrium. While the dynamical swirling defines a large-scale mixing length, the magnetic stresses acting alone cause the magnetic field gradients to steepen without limit when the field is allowed to relax to its lowest energy state. Okay. Proof. He imagines a situation where you start from, so here is the photosphere of the sun, here's the photosphere of the sun. So what he's done is taken a loop and he's basically straightened it out because, it doesn't change the ideas one is trying to address here at all. And then he holds one of these fixed, say this one, and then he allows the Japanese tourists to intertwine. So each one of these Japanese tourists, the soldiers at the other end that the Japanese tourists are watching, they have their field lines glued to their rifles, and they're not damn well moving. The Japanese tourists, however, want to take a picture of various angles, and they wander amongst each other, and with their cameras, they end up in a situation like this. The field lines get tangled. And unless order is imposed on the Japanese tourists collectively, his argument is that this thing must form discontinuous fields, which you can sort of see from that cartoon. How does that work mathematically? Well, we have the force-free equilibrium given by this guy, okay, and we have the zero diffusion, so we're not allowed to snip any of these field lines at all. That's the condition from the fixed topology. And then we also have this from the solenoidal condition. The magnetic field, the gradient of this thing called alpha is 0. This is a local statement. If I start off from here and I have a value of alpha, this is saying that value of alpha propagates all the way from here all the way up to there. It's constant along a field line. Remember, the topology is fixed. If I now look at its neighbor, that has an entirely different value of alpha. These are what known as, these are related to what they call the characteristics of the equations, partial differential equations. These are real characteristics. There's no way that in a hyperbolic system of equations that this real characteristic knows about the neighboring one. So this guy here can be twisted that way. The other one can be twisted the other way, and they're neighboring each other. If that's the case, then you have a current sheet. I'm almost getting to the end here. There are mathematical proofs which I don't want to go over, but that's the essence of what's going on. You fix the topology, but you allow the sun is anything other than tidy at the foot points. I think you have to agree with that. I mean, the kind of stars that Oleg was talking about are tidy. And they live, those fields live 10 to the 9 years or so. So nothing really is going to happen to dissipate them. The sun is untidy as convection. Here's the argument about the alpha effect, about the alpha parameter. There is no requirement that that be continuous from one field line to the next. Okay? Another view is that simply we've got an overdetermined system. We have one set of equations describing the force balance and another one describing the topology, and those can only be made to mesh if you allow these tangential discontinuities to occur. So what does this mean? Here's the tragedy of MHD. It's very straightforward. The tragedy is simply that ideal MHD dynamics, in the presence of untidy fields, in a low beta plasma, leads to the formation of tangential discontinuities. But these things can't form in the presence of a small finite resistivity. So in trying to become singular on time scales comparable to the Alfvén crossing time, the Maxwell stresses make steeper gradients until the MHD actually causes its own demise, the idealness. So it's going back to what Fausto said about, in a way, that the turbulence leads to these diffusivities of a certain magnitude, irrespective of the actual real diffusivity measured by collisional processes in the internal plasma. The beauty of this thing is, that this leads to a birth of a new area, and that is that we gain a theory in which we can account for the magnetic field changes and the dissipation and the heating dynamics, and we get fast reconnection out of this kind of thing. And this may be the thing that controls the heating of the corona. Even in open field regions where you don't have a fixed boundary above, it takes a finite time for the Alfvén waves to propagate their stress information, and in the time it takes, a little bit of motion here could be sufficient to generate a discontinuity somewhere. Most of the theories of coronal heating, wind mechanism heating, invoke getting to small scales. Parker's argued, and that's because you've got to find a way to get the energy dissipated. And Parker's arguing to us that it forms naturally as a result of its own basic properties. The non-linear form of the Maxwell stress tensor is everything. So, in conclusion, I would say that we've become accustomed to seeing the sun vary. There's a flare. Okay, you know, we get bored with these things. Only if they're going to hit our satellites do we get interested in them. But, you know, I would like to look at this from the point of view of, you know, trying to identify what it is physically that's going on. And so I think this is all of what solar and heliophysics should be all about, is the dB by dt, as I said at the beginning. And there are various unexpected things happening. And I would say that, I don't know why that happens like that. Oh, well. Just to finish that. Oh, great. Here's a review of the entire talk. So I hope I've drawn attention to what I think are some important problems. Yeah. And I want to thank you for your attention, and please talk to me. I will be leaving tomorrow morning around 11, so my email is available. I love talking to students. It's what I want to do for the rest of my life. I'm tired of working in a national lab. So please bug the hell out of me if you have anything that you want to ask me about. I'll be very happy to interact. I have 4 of them right now from Montana State University that I got to know quite well. I'd be happy to include anybody here that might be interested in, you know, I'm not going to solve problems for you, but I might be able to pose some difficult problems for you to do. So thank you very much. I want to thank Jorge for the invitation.